Alright, time for another DraftPhysics.com video presentation. Ooh, I have to fix that. Alright, that's a little better. So anyway, Franklin Hu has made another video regarding kinetic energy, and frankly, it's not very well thought out, and it's just, creating, in my opinion, noise. Now, he's claiming I just make rant videos, as he's called them. Talking about levers and how levers prove the kinetic energy theory can't be the truth because levers mean we can make free energy really, really easily. And we can't do that. We can't make it at all, let alone make it easily. Alright, so there's some things that could just, you're doing an experiment, you're saying, I want to do the experiment so I figure out how much energy something has. So as I've pointed out, Joule is rather famous for devising an experiment that can actually do that in some sort of meaningful way. Now, the trick is Joule did all his experiments by dropping weights in gravity. So the obvious connection to 1/2 mv squared or mv squared is created because all the experiments are using gravity and distance as a way of defining something's energy, and you can't do it that way. So anyway, alright, so the obvious thing I've pointed out is if I shoot two things in space, okay, and I give one twice the energy, okay, it's going 100 miles an hour and the other one's going 50 miles an hour, I know exactly what's going to happen, okay? I mean, the one that goes 100 miles an hour is going to go exactly twice as much as this one goes in the same amount of time. So in the same time, we're going to get exactly the same result. And it doesn't even matter if I don't even bother with time, and I just say at any point, it's always going to be the same amount because I'm not going to run them out of energy because I'm not going to be testing their energy, frankly, right? I'm just testing how far something that goes 100 miles an hour goes and how something 50 miles. I'm not taking their energy away. They still have all their energy. So, as I pointed out, you can't really do an experiment where you just launch things and let them fall because they have to fall, right? The one with half the energy has to fall here, and the one that has twice as much, it has to fall here because gravity is a consistent force and this velocity is a consistent force, and the air resistance is minimal. Air friction isn't much. Now, ground friction is something, okay? Now, for Franklin's video to mean anything, he has to have good reason to believe that friction, because he's going to use friction to collect the energy. He's going to take the energy away from the object. So he's going to shoot the object and have it, and it's going to have energy at 100% here, and he's going to drive it all the way to 0% energy. So like in a Joule experiment, he's going to extract all the energy and have it as something he can measure. Now he's using distance and saying distance measures energy, and that every little inch of distance you consume the same amount of energy. So for every little foot I pull out exactly the same amount of energy. So I can use distance to tell how much energy something has. How far it goes across the floor is an accurate way of measuring how much energy something has. Now I've attempted to argue that no, you're just doing the same thing as gravity is doing. And what you'll find is, okay, you can have two things. Okay, one thing is twice as fast as the other thing. So we have twice as fast versus one speed, velocity. Let me draw that in some way. Here's a little v, and this is twice the v. And the argument is that, yes, of course, the thing going faster will go further before it runs out of energy. And the question is, does it go 4 times further, or does it go twice as far? Now, obviously, I'm arguing that because of gravity is, as Galileo found, so this is something that's 1,600 years old, that in the first unit of time you do that much distance, in the second unit of time you do 3 units of distance. 1, 3, for a total of 4 when you only went twice. It's only twice the time. Alright, you're in the gravity. And when you hit the ground, you're only going to have twice the weight. Okay, so these are truths, okay? So, yes, you have twice the velocity, okay? It'll take you twice the amount of time, and you'll have twice the amount of weight. And yet the only thing these people pay any attention to is this 4 over here. Well, the 4 is a dodge because part of the time you're going fast through the gravity. You can't collect something when you're moving really fast through it. You can't collect it. So gravity's falling at a rate, a constant rate, and you have to collect it. Well, in this 3, you went really fast, so you can't collect 3 times as much gravity here because your bucket's moving really fast through the gravity, and it's only in the gravity for 1 second of time, okay, even though it's 3 units of distance. So this should be a D here, sorry. So yeah, and the same thing happens on the ground. Gravity is the way you're creating your sink. You're extracting the energy by using gravity to extract it, by essentially, the object is essentially throwing itself into the ground to lose its energy, okay? And it's going to throw itself based on these facts of gravity, which is, it's just going to matter about how much time. So what you'll find in the experiment, okay, so he does the experiment, and this is essentially, he came out 1.87 or something instead of 2. All right, but it's really much closer to, obviously the right answer would have been 1, okay, and he didn't get the right answer, which would have been 1. Right? Yeah. Well, it depends on how you do the math. The point is it's much closer to it being close to the squared function, the 4 times the distance. So he didn't give us the actual numbers, but that's what the numbers are basically saying, is that like this went 20 and this only went 5. Okay, so this one has half the velocity but only went 1/4 of the distance, indicating that somehow the thing with more velocity has more power or capacity to do work. And no, all it has is a gravitational advantage, and that the sense is that what if he timed it, if he timed how long it took for it to go from 100%, where's my percentage here, from 100%, how long it took it to go to 0%, then he'd find that, well, it is 1/2. This will take the same amount of time. This will take 1 second, and this will take 2 seconds. So even though it's supposed to have 4 times the energy, it only took twice as long. It only traveled for twice as long. So you should measure it by distance. Yeah, you'll get this 4-to-1 relationship. If you measure it by time, time will say, no, it's just 2-to-1. So again, you get exactly what gravity does. Because it is gravity. The friction is being caused by gravity. Gravity is creating the friction. So the bias of gravity, that is, it's all about time, is clearly dictating how much friction you're losing. So it's how long you're you're in friction that decides how much energy you're disposing into the ground. So so instead of getting a 2-to-1 relationship, you have a 1-to-4 relationship, and you have it even though it's only twice the time. So that's the key thing. It's basically telling you, yeah, there's something wrong there. So if I use just strictly momentum, and I said, mv, so I just said, okay, when does the object lose half of its velocity, right? Because that would be an indicator of whether this is a linear, okay, whether friction is even. If I go to find out where, so it has a velocity of 50 miles an hour here, it should have 25 miles an hour here. So if friction was even, that is, it took the same amount of energy per inch, you would expect that it would have half its momentum lost on this side and on this side. Those equal distances should consume the same amount of its momentum. And the fact is, it doesn't come out that way. Okay, it doesn't lose half its velocity until it gets here, okay, which is the same distance as this distance. So it's, this is replicating this, and this, obviously this huge 3 here is, and again here. So you're obviously, when you're going fast, you're only losing like, half your velocity in this entire big chunk. So this entire big chunk only consumes 1/2 of your velocity. The other half of your velocity is consumed here. So you're going 25 here. So if you're going 50 here, you're going 25 after you're 2/3 of the way down the track. You're not going 25 until you get 2/3 of the way down the track. And then you'll be exactly in the same position that this one started with. This one started with 25 miles an hour. This one will be at 25 miles an hour after it's a 3/4 of the way down the track. Then it will do that unit of time and friction. It'll incur the same exact friction because it's going the same exact speed. And obviously when it was going much faster, it covered a hell of a lot more distance, okay, and only gave up half of its momentum. So right there you have a proof right there that it didn't give up half its momentum at the spot it should have, which was the halfway point. So it's obviously telling you this friction isn't linear. It isn't fair to both fast and slow things. It treats slow things differently than it treats fast things. And then you can do just a simple logical test. I think I'll erase this. Be back. Alright, well, generally speaking, I just have to say I'm just so unimpressed by the intelligence of people communicating on this subject, because this really isn't complicated. The very fact that I have to sit here and explain that friction is the process of you losing your energy. You're giving it to something else. Just like a bowling ball hitting pins. It has energy, it has momentum, and the fact is that it will give its momentum to the pins and it will run out of pin hitting energy. It will lose its energy because it gave it to the other objects. And that friction is doing the same thing. It's taking the energy of the object. I mean, duh. There's not some special counter friction force. There's just contact, and it's like you have an electrical potential and something touches you. Now it can take your charge. It can take that potential. Yeah, jeez. So look, the simple thought experiment is I could just create a platform, okay? So this is a piece of road, and I take this section and I put it on a spring, let's say. It doesn't really matter how I do it. So this section can move up and down. It can measure how much force is being applied, okay? It's a scale, essentially. And it's just going to measure how much force. Now, logically, all of you have to know that if I roll a cart across it, okay, and I roll it really, really slow, okay, the cart is essentially going to get weighed on the scale, right? The scale is going to bend down, it's going to weigh the cart, okay? It's going to feel the full pressure, the full mass of the cart, and it's going to say the cart weighs 100 pounds. So it's going to collect all of the potential, gravitational potential. The thing will no longer, okay, be... I'm just saying it's going to collect all of it, and you're going to see the actual weight of the car. And now the faster I move it across here, right, so I can pull it really slow, and I can start off at 2 miles an hour, and then 4 miles an hour, and then 8 miles an hour, and blah blah blah. And you have to understand that as I move it faster and faster across this scale, it's going to weigh less and less and less until it weighs nothing at all when I go fast enough. So the faster I go, the less per foot. Let's say this is 1 foot. We know the friction, okay, is a hell of a lot to start with because you're pulling a huge amount of weight. And the weight is essentially a description of an amount of force or pressure. So you're collecting a huge amount at the slow velocity, and at the high velocity you collect nothing at all. Okay, I go fast enough, this registers, 1.7 ounces or something. And you can just understand it's just completely linear in the sense the faster I go, the less friction I'm able to produce, the less weight, the less contact I have with this spring mechanism. This thing feels less pressure. I cannot take energy from the object because I don't have sufficient contact with the object to take any energy from it. So obviously your contact with a surface is completely dependent. So this is like saying in an electric circuit, just how many wires do you have carrying how much amperage? And the more wires, the more amperage, right? So if I don't have sufficient wires, I can't produce, I can't get the energy into the other contact. So the better the contact, the better, the more efficiently I can dispose of my energy. And the less contact, the less I can dispose of my energy. So obviously the cart loses less velocity to the scale and the ground the faster it goes. I really shouldn't have to say more than this, right? I mean, it's quite obvious the friction isn't the same, okay, no matter what speed you're going. The faster you go, the less contact, the less friction. Just a fact. Now, it depends on what the surface is, right? I mean, if I could make the surface a bunch of sawtooths or something, and there could be a special circumstance where I actually rip the thing to pieces because it's going fast, and if I allow it to go slow, it can just go over the little points without losing too much. So I can create some special circumstance where speed is a disadvantage, but the fact is, just every common friction circumstance, obviously this is gravitational weight that you're applying to the surface, and it's just about how long you're in the gravity. So the amount of time will dictate how much you lose to the surface. So that's why when you're going 100 miles an hour, you'll go 4 times further, but it'll only take you twice as long to do it. You'll only be in the gravity twice as long. So you're going 50 here, you're going 100 here. Again, it's going to be, yes, you'll travel 4 times the distance, but you'll only be in the gravity twice as long. You'll only apply to the surface this twice as much weight will you apply to the surface. And it's the weight you're applying to the surface, how much weight you apply to the surface, will decide how much energy you lose to the surface. So it's only twice as much weight on the road when you go 100 miles an hour and then when you go 50. You only apply twice as much weight to the road. I don't think I should have to say more. So we'll play a little bit of Franklin's video, but the whole thing is really quite annoying because this is just adding noise. Okay, so he made his big announcement based on a video that obviously was garbage, or an experiment that was obviously garbage, because he obviously didn't get the right velocities. So even though he says he knows how to do experiments and he did it well, he obviously didn't do it very well, because now he's done it in a new way where he's more certain of these velocities, and they came out the way you would I would argue you would expect if you understand that friction's not a fair force, that friction doesn't take from every object the same amount, because it depends on how you're creating the friction, right? If we had a friction that was being applied from the sides, then it wouldn't be gravitational, and then we might be able to make these arguments. This is why you have to do the experiment with, smashing into a spring or smashing into clay. Now, I could draw that. I could draw a spring and just give you the simple argument that if you go into the spring with twice the velocity, okay, even though it's 4 times the distance you might have dropped it in gravity, it's only going to weigh twice as much. You go 4 times higher, it only weighs twice as much. That's such a proven fact. I shouldn't have to prove that. I have personally done the experiment and it works perfectly. So yeah, 4 times the height, it only weighs twice as much. It doesn't weigh 4 times as much. All right. Whatever. This, like I said, the lever argument should end this conversation. If you're going to find some other way to test how much energy something, again, Joule invented a water tank, with a spinning turbine, so he could, turn all of the energy into heat, and then he could just measure the heat and calculate how much total energy something has. So you have to do it a little more sophisticated than this. So he's basically saying here that, oh, look, you can do these experiments. If you keep doing them wrong, okay, that's not helping. That's my argument. So if you don't engineer your experiment to extract the energy evenly and completely, then what's the point? Because you're just creating more deception.
And with this variety of data, you can directly test to see whether doubling the speed, quadruples the kinetic energy. So
So you can't unless you have a mechanism that isn't variable. That is, that doesn't give advantage or a bias. It doesn't have a bias. So you have to create a way of collecting the energy that's absent a bias for velocity.
You can pick say we've got 25, and that measures out at 12 and 12 and 3/4. So, so it should, at 50, it should be 51. So we've got what, like 49 here, and so it's 49. So it's falling short, is what it's doing. So it's
So that seems a minutia point, 49 to 51 or something. So obviously it's fitting much closer to the pattern of mv squared than it is fitting to the pattern of momentum, which would mean that the distances, it would only go twice as far. And it's obviously going much further because it's going much faster and it's having its energy extracted at a much slower rate while it's going faster. So again, if he measured the time, he would get the 2-to-1 relationship. If he measured the impact weight, he would get the 2-to-1 relationship. So if we just crash the cars into a spring, the faster car is not going to compress the spring 4 times as much. It's not going to show you that it has 4 times the energy. So mv squared will totally fail if you just crash the things into a spring. If you crash them into a spring, something going the same weight going 50 miles an hour, the same weight going 100 miles an hour, they're not going to compress a spring 4 times as much. The 100 mile an hour will not compress the spring 4 times as much because we already know it's only going to weigh twice as much. I mean, it's a well-established, proven, I don't have to prove that fact, okay? The scale will not go 4 times as much, even though I went 4 times higher. Twice the velocity will create twice the deflection, So if the deflection is there for 50, that's going to be 100. 100's not going to be off the scale. It's only going to create twice as much weight. So this is all garbage because the foundations are garbage, because the underlying assumptions are garbage. You can't use whatever you would call it, gravity-imposed friction as a measure of extracting energy because it doesn't do it evenly. You have to find some other mechanism, bowling pins, some other example, some other way to measure how much energy something has. You can't use friction because it's not a fair force. It's not a force at all, but it's basically just saying, what does gravity say? And we already know that gravity has that built-in bias where obviously it's about how long you're in it, and if you're moving very fast, you're not in it very long.
Not quite x squared, which is
I mean, obviously, if I'm getting paint, it's just these are just simple arguments. If there's a paint sprayer and I move across this paint sprayer twice as fast, you can understand it's only going to get half as much paint on it. And gravity's doing the same thing. It's about how long you're in the paint spray. So, and your mass is going to collect it based on your mass. So if I use different size things, but we're using the same size object, so it's the same size object. I move it at a speed across a paint sprayer. If I move it at twice the speed, I'll get half as much paint on the surface. Come on. Duh.
what this is showing is that it's x squared is generally overshooting what is actually measured. So once again, I'm not exactly sure what to make of that. That could be...
So now he's just, if he had done this experiment first, he would have said, oh, mv squared is proven. So now he's just trying to reclamate his first experiment where he made his declaration that he's proven it doesn't work, and he proved it based on pretty poor experimental apparatus and wrong assumptions. And so now he's fixed some of that, and he's getting the results that you would expect, okay, logically, because gravity is controlling the friction. So as long as you let gravity, as long as gravity is in control, you're going to get the 4-to-1 relationship. If you do a fair fight, you're going to get the obvious 2-to-1 relationship. Momentum wins, except in gravity. It still wins. The object goes 4 times higher and it comes back down. It still only has twice the energy. Twice the energy lifts it 4 times higher. That's just a fact. I can use the lever and prove it. I can have the same force over here on the lever. I can put the 2 mass here. I can move it up 1 unit of distance. I can put the half mass here, do the same thing with the lever, and it'll go 4 times higher. I can take the same mass, and it's going to go 4 times higher.
An effect of friction. But once again, the point of this series of videos is to just show how you can do experiments and to show.
So it's not showing how to do experiments, it's showing how not to do experiments. This is exactly the point. Everybody's relying on these goofball amateur experiments when no, all of this should be done really well, and it should be understood that yes, you can't collect energy any way you want to. You have to collect it in a rational way. So they keep doing experiments that have catches to them. Brozo keeps doing his drop round things into clay. He still hasn't accounted for the fact that the shape of the object does make a difference. And he doesn't care to hear that. He doesn't want to know that's the truth. And then the Mythbusters video, again, is a pretty clear demonstration that you do the experiment fairly well and there's no sign of the kinetic energy theory being correct. The clay of the 100-mile-an-hour is crushed exactly twice as much, not 4 times as much. And it's logical because we know the weight of the object is only twice as much. It only weighs twice as much. 4 times higher, you drop it from 4 times higher, it hits the ground weighing twice as much. The scale proves this. Whether I drop it this way or I drop it this way, the scale proves it. So why is this an argument? Rational people shouldn't be arguing. Twice the weight is 4 times the energy. That's absolute nonsense.
So that you can actually
twice the time, twice the velocity, twice the weight. And because distance says, oh, I can go 4 times faster because I'm going faster through the force. I'm plowing through the gravity and evading it by going really fast through it. So it's not pushing me into the ground as much. Again, you can't intuitively know that the faster you run across like water or mud, the less you're going to sink into it. Like theoretically, you might be able to run across a pit of quicksand if you could go fast enough. There's probably a better example. A very rickety bridge. If you can get across the bridge fast, okay, you only put a lot less weight, total weight on the bridge. You can't say and concede, oh yeah, that's true. Come on.
Do an experiment that's trying to directly test whether the kinetic energy formula is true, because this whole thing was motivated by the fact that there wasn't any videos on YouTube that actually tried to directly measure.
Yeah, and there still aren't, and that's the problem. There aren't any worth paying any attention to because they're not done well enough. Again, really the argument is so simple. The simple videos I've shown where I've shown a lever perfectly oscillating with twice as much kinetic energy on one side than on the other side. Right there, the conversation should be over. Because anybody who understands what an oscillation is must understand that there can't be twice as much energy on one side of the oscillator than there is on the other side. It can't oscillate that way.
The kinetic energy formula by just measuring the velocity and then trying to find a proxy for the kinetic energy.
All right, so whatever that, I don't even know what that means, to try to find the proxy for the kinetic energy. You're just trying to measure the energy. There's only one kind of energy. There's only energy. And the fact is, momentum works always. Kinetic energy never works almost, in the sense that, yes, it only works when you're doing one mass into one mass conversions. Every single time you convert energy from a lighter, faster thing to a bigger, slower thing, you lose energy, and every time you do the slower thing into the lighter thing, you're gaining preposterous amounts of free energy. Frankly, it's idiotic. And I shouldn't have to spend 2 frickin' years explaining why it's idiotic, because it's idiotic for so many damn reasons. All right, I have to pause. All right, I should be back. Let's finish up. Play a little bit more of this. Blah, 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 blah.
In my case, I used how far the car travels, presuming that it loses energy by friction at a constant rate.
Okay, and why would you presume it, especially after the first video where I already pointed out my objection? Did you solidify that? Did you research that? Did you find any way to see whether this whole idea of using gravitational friction, again, if you use some other form of friction that doesn't depend on gravity to create the contact, that is bowling pins or some other mechanism. Even bowling pins is a little dicey because, yeah, they have to move against gravity, they fall over. So you have to find something that isn't fiddled with by gravity, because gravity is not a proportional force. The force that pushes on the feather and the force that pushes on the 10-ton weight is not the same force. Yes, they fall at the same rate, but the amount of energy that goes into the 10-ton weight is monstrously huge compared to the amount of energy that goes into the feather. Damn. Quite obviously. Because when they land, you're going to see the energy come out of the objects. The only difference between the 10-ton weight and the feather is the energy that went into the object. What gravity gave it in the distance they fell. Jesus. Oh, dear. Didn't play.
Which may or may not be a correct assumption. But here's the data.
Okay, so it may or may not be, but here's the data anyway. Here's some more noise for everybody to have to see through to get to the right answer. So yeah, this isn't productive. Sorry. Either do it all right or don't do it at all, kind of a thing. We don't need more noise experiments.
Yeah. And once again, I appreciate all the comments and all the ideas.
I don't think you do, but I sure don't. But whatever. Well, look, it is a serious thing. This is a serious subject, and the very idea that people have been comfortable for 300 years sitting around going, "Oh yeah, momentum's a thing," and yeah, kinetic energy is a thing. It doesn't make any sense. I mean, how can you say they're both things? Okay, except one's real and one's somehow, yeah, not so much.
And we will be continuing this on with another series of experiments to see whether, for example, friction is lying to us.
Well, it's not that friction lies. I'm just saying just obviously gravity creates this Galilean, okay, 1, 3, 5, 7 relationship. The faster your velocity, the more distance you travel, but the less force you collect, because you're going faster across it or faster through it. You're applying less force.
So that's all we have for now. Ta-ta.
All right, well, whatever. So, like I said, I like Franklin. It'd be nice, if he was a little more engaged. He did another experiment with a little magnet around a Venn diagram. And there's no context, no nothing, no comparison to a control, no comparison to anything else, no way to really judge whether we're seeing anything that means anything at all. These aren't good experiments. You got to do experiments that have a little more thoughtful context than this. Frankly, you're just making noise. Franklin. Yeah. So anyway, sorry this is a bit harsh. But yes, I've been in this for 2 years, and these kinds of bad pieces of crap arguments and evidence just doesn't do the subject any good at all. This does not make things clear. It just muddies the water, and completely unnecessarily, because everybody should be able to agree that the fact is the faster I walk across a trap door, the less likely I'm going to fall through it. It shouldn't be anything anybody disagrees about, that I'm going to be applying less force to the trap door if I can get across it faster. Damn. And if that's true, then friction isn't a fair force. Alright, till the next time. Gravitational friction. Till the next time, and such, and so forth and whatnot. See, you just got to come up with some other way, like little things that the thing hits, you know, little levers or something, or a bunch of little doors, and so you let the things hit the little doors and see how many doors they knock over. You have to find some other way to collect the energy where gravity doesn't muck it up. Alright, now it's enough of the video. Alright, so we can get rid of, oh, we already got rid of that. I'll get rid of it again then. Let's get rid of it again. Oh, that's the wrong one. This is the one I want to get rid of. Yeah, and then I want to get rid of that. And then I'm supposed to still be here. And then I slowly fade away. That's the way I'm supposed to do it. Okay. There's something to be said for professionalism. Yeah. Till the next time and such.